Hello and welcome back. I want to continue looking at this last example where we had a function that we showed was not continuous. Oops, didn't mean to erase that line. And we showed that it was not continuous at 0 because our function doesn't exist at 0. We can't plug 0 into the function, so we would automatically think that it's going to be discontinuous there. It's broken. So what about in other places? Well, we can see that as far as we extend to the right, as long as we are at positive values of x, our function looks exactly the same as 1/2 x, which is just a nice polynomial. It's just a straight line. It's not doing anything crazy. It's just going up a little bit slowly. To the left, on the other hand, we have x squared, which again is a nice smooth function. It's not doing anything crazy. It's going up, say, faster and faster and faster. But at the same time, I could continue just drawing this parabola for as long as I wanted to. So here f is continuous to the left, because this is just going to be a straight line. There's nothing going on. It's going to be continuous. Sorry, to the right and to the left. This is just a parabola. So this is going to be continuous on everything from -infinity up to 0. So that's everything to the left, and everything to the right from 0 up to infinity. So whenever we have a function, we can look at where is our function continuous, and here our function is continuous almost everywhere except for at 0. And let's look at one more. We've got 1 over x squared. So if I'm graphing this 1 over x squared, if we just plug in a few points, let's say at 1, 1 divided by 1 squared is 1. 1 divided by 2 squared is a fourth. 1 divided by 3 squared would be 1/9. But if we plug in a half, 1 divided by a half squared is a fourth. 1 divided by a fourth is 4. So it's going to be way up there, and the shape of this is going to be something that looks like this. So as we come up, we're getting closer and closer to the y-axis, and as we come over here, we're getting closer and closer to the x-axis. But if we square numbers, all the negative numbers become positive. So it's essentially the same thing on this side as well. So I do want this to be nice and smooth, and then we're coming up. So the question is, where is this function going to be continuous? Well, again, at 0, I can't plug 0 into this function. F of 0 does not exist, so f is not continuous at at x is equal to 0. And this is again, we just can't plug 0 into the function, so our function is automatically discontinuous. We'll have to lift our pet up. Another way to kind of see this is what would happen if we tried to take the limit here. So if we take the limit as x approaches 0 from the left-hand side, as we come up, our function is just getting bigger and bigger and bigger. As we divide by smaller and smaller numbers, if you divide by a small number, you're going to get a big number. So it's just getting bigger and bigger and bigger. This limit is actually going to be infinity. And then we get the same thing if we're coming from the right-hand side. We're just going to be going up and up and up, and this limit is also infinity. So since both these limits are the same, we can say that yes, this limit, the limit as x approaches 0 of x is equal to infinity. And whenever this happens, if we ever have the limit of x is equal to infinity, can we ever get a function that's just equal to infinity at that point? So if I plug in a 0 into any function, could I get infinity? And the answer is no. Infinity isn't a number. If we ever have a limit equal to infinity, or negative infinity for that matter, our function is not going to be continuous there. Again, just because this can never happen. Whenever you plug a number in, you have to get a number. Infinity isn't a number. So limits can be infinity, the function value can't. So this is another indication why our function is going to be why our function is not continuous. And here I want to do say one final example. So we have the function x squared minus x minus 2 over x plus 1, and we're just going to be equal to 1 when x is negative 1. So I want to try to draw this function. And right away, I look at this and I go, this looks hard to draw. So let's simplify this a little bit. If we have x squared minus x minus 2 divided by x plus 1, this is going to be the equation of the line everywhere where x isn't 1, which is good because I can't plug, negative 1, because I can't plug negative 1 into this function. If I try to plug a negative 1 in, I'm dividing by 0, which I can't do. So let's see if we can't simplify this. The top here will actually factor, and this is going to be x plus 1 times x minus 2 divided by x plus 1. And this simplifies, and it's going to be x minus 2. So this function is just equal to x minus 2 as long as x isn't negative 1, because I can't plug that one in there. So let's graph let's graph x minus 2. So our slope is positive 1, and our y-intercept is negative 2. So we'll go up 1 over 1. Oops. Let's see here. There. This should be a straight line, so I'll just do as best as I can. And we have to remember that this is not going to be the function value at x is equal to negative 1. So at x is equal to negative 1, we have an open circle. So right away we can see that this top part is not really going to be continuous because we have an open circle there. However, we fixed it with the other part of our piecewise function. Oh, maybe I should have done this instead. This is going to be a better example. I miscalculated that earlier. Oops. Okay, now we fixed it. Okay, so let's look at this at this function instead. I apologize. So if our function value is equal to negative 3 at x is equal to negative 1, at negative 1 we come down here and we are just going to be equal to negative 3. So we fill in the gap that's missing in this top equation by saying, oh, we'll just have this be equal to negative 3 there. And we can see that, from our picture, this should be a continuous function at negative 3. So let's test that. Let's take the limit as x approaches negative 3 from the left. So again, if we're not equal to, I did the same thing again, didn't I? If we approach negative 1 from the left, so as we approach negative 1 from the left-hand side, we're going to be following this part of the equation because we're not equal to negative 1. And this part of the equation looks like an x minus 2. So we're going to be approaching negative 3. The limit as x approaches negative 1 from the right-hand side, again, if we're approaching from the right-hand side, we're not equal to negative 1 yet. We're not plugging in x values that are negative 1, so we're using the top part of this fraction, which is the same as x minus 2. So we're approaching down here. So the limit of f of x is going to be equal to negative 3 as well. And if I just plug in negative 1, again, I'm not using the top part of the fraction anymore, top part of the function, because that's when x is not equal to negative 1. When x is negative 1, our function is just -3. So f is continuous at x equals -1. So even though we look at this function and we go, oh, x is equal to, we can't plug -1 into this function, it's still continuous there, simply because it's sort of, the gap is filled in by the next part of the piecewise function. So we do have to be a little bit careful. And I do want to talk about, just in general, what some continuous functions, there's some examples of continuous functions. So polynomials, when we think about graphs of polynomials, so some polynomials are just going to be straight lines. We might get parabolas. We could get cubic polynomials, which will look like this. And the thing is that all polynomials, they exist everywhere. They're nice, smooth functions. These are all continuous everywhere. So this is quite a nice. These are quite nice continuous functions to have in your back pocket. E to the x looks something like this. Oops, it should be exponential growth, so it should come up a lot faster. But again, it's basically just a straight line. Not a straight line. It's just a very nice, smooth, curved line, and it just starts going up and up and up. There's no discontinuity in here. There's no number that I can't take e and raise it to that number. So this is also going to be continuous on -infinity to infinity. And in fact, if you take b to the x power, it doesn't matter which one you're looking at. Natural log of x. This one we have to be a little bit careful of, specifically because the natural log is not defined for some numbers, but the natural log looks like this. And one of the nice things is that the natural log and the exponential function are exactly the same. They're just flip-flopped. Here we're starting, we're getting closer and closer to the negative x-axis, and then we're sort of going up. Here we're close to the negative y-axis, and then we're sort of shooting off. So these functions look exactly the same. They've just been reversed, as if in a mirror, sort of across like this. So since e to the x is going to be continuous, the natural log of x is also going to be continuous, but only over here. So again, this is continuous on 0 to infinity. Again, because I can't plug a 0 into the natural log of x, and I can't plug negative numbers in, if the function doesn't exist, it can't be continuous there. But wherever the natural log is defined, it will be continuous on that side. Sines and cosines. These functions are quite nice. The sine just does something like this, and the cosine looks nearly the same. There's no discontinuity in here. It's just this wiggle that goes forever, and these are going to be continuous everywhere. Again, there's no number that we can't plug into sine or cosine, and there's no places where there's going to be any breaks in the line. Tangent, on the other hand, looks different. So tangent looks something like this. And then it repeats. We have this asymptote here, and then it sort of repeats. So as we draw the tangent, we can see that, yeah, we do have some discontinuity in here. So for instance, in this range right in the middle, this is continuous on negative pi halves up to pi halves. So once we hit pi halves, we have to jump from positive infinity down to negative infinity. And just mentioning infinity should ring some alarm bells and say this is probably discontinuous. There's a couple more types of functions that I will look at in the next video too.